is about the quantum algorithm. So we know quantum computing have get into the stage where we are talking about how to use quantum computing to take benefit of the computing. There are many other areas. My research is funded by U.S. National Science Foundation, several grants over there. Give you some update about the status. I will tell you what my research is focused on. Yesterday is a special day, everybody knows, right? It's Pi Day. You look at the PR code that from SoundCloud. I think 12 years ago, I was playing around to compose the music, the Pi music. Basically, I mapped the Pi digits to a music note. You scan, take a listen. The reason I'm mentioning this, because you look at the people here, I think most people at least know three. The last one, I think the U.S. Senator Hatch. All four in common. Why in common? They play instruments. Everybody plays more than one instrument here. So again, even our iPhone is benefit from Steve Jobs. Love music. He wanted to store music into the electronic device called iPod. Now it's iPhone. So that's the idea. You look at the bottom, I think that's the Pi digits, 100 digits, of course, without 3. So if you can guess. They are related. Why I'm mentioning about the Pi, I mentioned about it yesterday. Also, there are something, if you study the quantum computing, the number theory covered a little bit about the numbers. It's a very interesting topic. For the current status about the quantum algorithm, basically we are talking about a QPU, CPU, and AIU. Okay, first one should be type of CPU, QPU, or GPU. Okay, the QPU is the quantum processing unit, and the AIU, the chip developed for AI. Okay, I said the type over there should be the GPU first one. Okay, I don't know everybody. We may have the different areas, right? If you use a Qiskit for quantum computing, remember on the IBM, the AI assistant. Basically, a lot of code you don't have to write. You just generate for me. You can generate for you. So convenient. Not mean we don't need to write a code because they're very simple code. You don't have to write every single line. You put a more advanced over there. When you look at the IBM QPU Heron, the second edition R2, you have the 156 qubits. So first one will be 133. 156 qubits is very recent. You look at my account on the lower right corner, I do have access. It's a little bit expensive, like tens of dollars per minute. It's expensive, but I can do the work. You don't need a lot of time there. That's why we are studying. Even the running time, even you have for example, even 100 per minute. So the idea is many programs, you don't run a lot of seconds. You can prepare before you send to the quantum computer. The algorithm execution basically follow the 4 steps. Mapping. You have a problem. You want to map to a PC, quantum circuit. Right? Currently, we write a program code, Python, C, but in quantum computing, because quantum circuit, you need to map that. That is not a very easy if you don't know this. You need to optimize, like a compiler, execute, and post-processing. So we're going to cover these processes. So for example, right, the pipeline, the initialization, right, layout, translation, optimization, schedule. So it looks like if you know OS, operating system, basically similar process. But there are the steps, right? Looks like the same, but when you run, really it's different. Let me move this one if I can. Give me a second. Okay. This one? Okay. Oh, nice, better. Okay. Give me a second. Oh, I want to move. All right, good. Circuit optimization. Basically, if you remember when we write programs, regular computer programs, we need to make sure use less memory, more efficient. This is the same thing. For circuit optimization, really you want to rewrite the quantum circuit, right? Quantum circuit, if you don't know, really programming. So basically, quantum programs right now quantum circuit is a programming part. Several steps, right? You need to know. If you look at the graph over there, the first on the left compared with the right. So the first is you have the H, right? H gate entanglement. The second would be swap. If you look at the simple, right? First step, second program is swap. If you swap plus the signal is Q2 to Q3. You see the sign over here. Oh, sorry. Okay. Let me see. Now listen to me. Yeah. If you see here, right, the signal from Q2 to Q3, the line, really swap and signal Q2 to Q3 really same as to the right is the Q0, if you to the left, right? Q0 to Q3. So what do we mean this optimization? So what is the big deal for this? If you know the cost, we know the program, right? Cost, the swap, you need at least 3 steps. Sounds like a regular swap, right? You need to store A to B and then swap B to A and store A to C, something like that. The quantum state is the same. If we remove the swap with 1 step, we save the, for example, very basically 3 steps. That may be more, right? So I think to give you some ideas, optimization. Why we need to optimize? Because the quantum memory is very limited. Qubits very limited. We cannot like we are using now. If you doing computing for a long time, you know what I'm talking about. So when I was writing programs many years ago, really you think about how we're going to save memory, how we're going to do a lot of things, right? Now people, I don't care. I use Python. I can write everything I like. Send over there, maybe slow, but I don't care. I can get it down. This is not there yet. We don't have the luxury on quantum computing. We have to save the resources. Error mitigation. This is a very interesting topic about error. With the digital, we don't have error. So in anybody remember recently or recent years, not recent, maybe 10 or 20 years, right? Your computer give you an error. I mean, error for computational error. No, never happened. Why? Because the digital you have a 0 and 1, right? You don't have no error. So if you look at the sound, right? Sound quality, you have by the Bose headphone, you see you want to get a better quality, right? You don't buy a $20 headphone, put on your head, you listen to music, that's a waste of time. Okay. So what is that? Because if you take a look at transistor, really that's called kind of like analog computing. So currently the computing we call digital computer. We don't see the digital anymore, but it is a digital computer. The things we use only the stable state, 0 and 1, while amplifier use the linear, hopefully, right? Linear step with the transition time, you may have error. So the quantum computer right now, basically the error, like analog computer, there are errors over there, a lot of errors. Give you an example why. If you look at the semiconductor based like IBM, their CPU is very small, but it looks like a picture. I have a picture that didn't show. I guess you can Google, everybody Google online. Like a refrigerator, beautiful, like a chandelier refrigerator, right? Don't be confused. That's not. The only thing, the chip is the same, similar, like we are seeing now. All the rest, like a refrigerator, get to the temperature close to zero. Very like a 272 or 3, like a Celsius, very low. So at that time, because we cannot get to absolute zero, there will be errors. But electromagnetic field interferences, you have a lot of errors. So the idea is we want to reduce the errors so we can do better. If you look at the left, right, the left I covered, right, to the right, give you some ideas over here, because the circuit, like you do the reverse circuit, that's the left. I covered the right side. You can see the on top one is the same one. We do the like a compile. The idea is what we do this here. It looks like, hey, what you have done is look at more complicated, more circuit. Well, save time because all the on the top one, the smaller one, really are basic steps. While if you look at the left one, that part you have a synod, you take more time, right? Take more time to execute. Basically, we did optimization to give you some ideas over here. And then quickly, I want to mention about quantum machine learning. It's a hard topic. There will be many people doing this. I have 4 students get the IBM the Master Award. They are doing quantum machine learning research. Basically, the quantum machine learning, you train the model on the QPU. You don't do anything, everything on the QPU, but you only train model on the QPU. You can run the other, for example, prediction, the other part on the HPC. There's called VQC, variational quantum classifier. I can show you something. They use neural networks. The idea is if you look at the middle idea, right? So how are you going to map regular data onto a quantum input? So that's the very big challenge. Fortunately, there are people doing this already. The example I showed you that's running on the quantum computer, you can see converge very fast, right? With the VQC, and you can this, of course, this you can do with the classical method. But I show you the idea is, hey, the classical method can be done, but we can use the quantum computer. On the other hand, if the problem getting very, very huge, the classical computer you cannot do with the classical computer, but a quantum computer take that advantage. You don't see now for this problem. So the VQC is a similar. You want to basically very 2 steps I mentioned earlier, right? They're the features. You do AI, machine learning, you want the features, right? You can take all the features you train, like you put the matrix, right? They're doing all the transformer stuffs. Here is you do mapping, map all the features onto the quantum input, first part. This is a small problem, not a big one. I give it to you. The second part is when you do I want to solve, set up the program. If you look at the bottom part, that's the program, quantum program, something like that. With some IBM called the simpler step, right? Quantum composer. like a music stuff. Right? So you can see here. You did get a convert. get to the part. So the VQC give you 60%, right? On the 60%, on the test set would be 50%. Not pretty good compared with the classical 90%, but still fine. Okay. I mentioned about the feature map. So feature map basically in everything in AI, right? Machine learning, is you want to map the problem into another higher dimensional space. So sometimes I'm not that religious. I can share with you my thought is if you get stressed, you could see a psychiatrist. They see some more dimensions you don't see, they can calm you. And maybe you go to church, right? Because God can see high dimensional, which we cannot see. That's we gotta feel better, right? Solve the problem. I think it's same as the feature mapping. Uh, if you don't see the problem for this first one, line or a dot, you don't know what's going on, right? Probably you can do this. Play, yeah, okay. You can do high dimension. You're gonna see the problem. The second one is the same thing. If you see the like a plane on the same plane, we should not, right? That's why you need it from the additional view. That's beyond the three dimensional. The third one is not like you feel miserable, right? But if we get calmed either by God or by whatever people, so we see that the pattern working actually. It's not something totally random. So I give you the idea is if something cannot be solved in certain domain, you want to do the higher dimensional domain. That's very common in AI, right? In machine learning. Okay, this is something new. Parallelism in hybrid quantum computing. So as we know, everybody agree, the quantum computing right now, it cannot be quantum computing chip alone, have to be hybrid, as I mentioned in the first slide. So you have a QPU, GPU. I want to mention how are we going to manage the QPU and GPU. Right now, I was at IBM earlier. On the top, you see classical QPU, they're doing this way. And right now, my research is really focused on pipeline. The pipeline technology, of course, we know everybody know every computer right now uses pipeline, the chip, CPU, GPU, use a pipeline. So I'm trying to use this one to further improve the performance on the quantum computing. It's a long way to go, but we just started. We got funded from the NSF right now. Another research I'm doing right now is, everybody know the QFT. Of course, you know FFT, right? The fast Fourier transform. Basically, the AQFT is that we want to give you some estimate, about how QFT can be executed faster. So go back about this. If you know the Peter Shor, professor at MIT, he's a great professor, invented the Shor algorithm, which can reduce the computation from exponential to polynomial. We cannot imagine. Of course, only on quantum computer. For example, if we know the RSA, we do the encryption every day. If you use a classical computer right now, you need a billion years. I said billion years to attack, very strong. But with quantum computer can be within minutes or even shorter. So this is the program I run. How we're going to improve the speed I'm going to mention in the moment. If you look at the bottom right, really the QFT is a recursion, right? Recursion, same as the other format. Okay. I'll go back a little bit about FFT. why FFT is better. We can do image processing, right? Back then. Now we can do very easily on the phone image processing. The idea is the FFT, DFT, right? Before FFT really benefited from this butterfly on the right. That butterfly transform the multiplication in n square before, right, to addition. Transform multiplication to addition. That's beautiful, right? So beautiful. Can be faster, of course. But there's overhead. The overhead is log n. So that's why the FFT get to from the n square to n log n. We know this, right? The original. 1D is the same. For the, I have a 1D, right? 1D is from frequency signal to addition subtraction. I said 2D is from multiplication to addition, but with overhead. For quantum Fourier transform, QFT, I mentioned it earlier in the slide, the Shor algorithm transform exponential EX, right, n-dimensional, to polynomial, A3. Polynomial is very fast. That can be done. The idea is very interesting. I hope we have enough time to cover, but I want to speed up. That's the Peter Shor. I was in his class. Of course, there are papers you can read. The idea is if you remember a sphere, the theta ex, right? The x is the theta over there. Really, on the sphere is the kind of angle toward the north axis, like angle, like a cone, rotating. But if you look at it from top, right, projection from the top, really the circle, you have the left and right rotation. So that's what happened. The QFT transform EX, right, e to the power of x, to addition and subtraction with the overhead. The overhead is the polynomial, N3. Again, you may heard of the PQC, right? Post-quantum cryptography. It's based on crystal. So we say, hey, if we have a PQC already, I want to mention about the security. First, we do quantum computing. Why we use the Shor algorithm? There's the security consideration. Right? The PQC looks like everything is good, but may not be my point. Why we have to worry about PQC? People said you don't have to worry. Well, it was wrong for the mathematician. I'm not against mathematician. I like math, right? Enigma, right? DS, RSA, and the PQC. Every time they failed, every time. I'm not saying they failed PQC for now, but my projection is, I don't know. So, okay. You may heard of the QKD, quantum key distribution, because the encryption, we're talking about the attack, RSA, really about the key, quantum key. So that's another ideas. Of course, there are concerns. There are a lot of informations, discussion over there. But this is another dimension of the security you can think about. I mentioned about the history, mistakes, right, made in history. So if something we cannot see, look from other perspective. So I mentioned about the first 1D, 2D, 3D, and n dimension. Give you some ideas. They see some equipment in my quantum lab. I have I think very few. I'm not the only one. Probably under the computer science department in US have the quantum single photon detection, the quantum key distribution of the devices in my lab. I'm also looking for people, if anybody wants to come to my lab for research, if any faculty, postdoc, PhD would welcome. For everybody, come would be have a full pay, even for the summer. Contact me if it's possible. This is the another technology that's also funded by the National Science Foundation. Applied a grant already. Recently published the Department of Defense, DoD, right? Department of Defense journal about the secure quantum network. One more? Yeah. Okay. So give me a second. Okay. Yeah. Quantum internet. I have moved. Give me a second. How many moved it? Yeah. We know the quantum internet, we have 7 layers. We have routers, switches, encryption, but also we know the challenge with quantum stuff. At the bottom, there's 2 books, and there's a QR code for the recent one. I authored. If you are interested, take a look. There's the second one, there's the new one. There's a chapter on the quantum stuff over there. Okay. I guess I want to stop here for questions. Thank you.